Continuing on from amp hours versus watts, let's look at how household appliances are rated. So here are two rating tags off two different appliances. They've got all the proper safety features to indicate that how they were created, that they've complied with various government standards. And they report power in two different ways. One way is to state the voltage and the amperage. Now this is 120 volts at 10 amps. 60 hertz just means it's pulsating electricity. The combination of these two is what gives you your power. So instead of seeing 100 watts, you might have what's written on the appliance 5 amps at 120 volts AC. The V is your voltage. It can be followed by AC for alternating current or DC for direct current. Sometimes the alternating current is just shown with the tilde here, a little wiggle to indicate it's oscillating electricity. What do we do with that? Well, we can take P is equal to V times I, and we multiply the two together, and we get 600 watts. Would be what the power would be on this unit. Now this one here just states it for you. It's already been done. So if you get voltage and current reported separately, you just multiply the two. This is like saying 5 cups of electrons every second, and each one of them came with 120 calories of energy. So it's like counting cookies but reporting the calories you consume. So this is the same as joules per second. These rating tags on these devices often come with a whole bunch of other electrical information, but most of it for our course is just the volts and amps we're interested in. Typically, we report power on devices, not energy. It's not possible to say how many joules your refrigerator is using because it never shuts off. It's always accumulating. You can only talk about the use of power and time together to get the energy. If I gave you $5 an hour for 3 hours, that's $15 I've given you. A power of 5 joules a second running for 3 seconds is the same as 15 joules. The 5 joules a second, however, would be written as 5 watts. What happens if you had 3,000 watts running for 4 hours? Well, you'd multiply those two together, and you'd get 3,000 watts times 4 hours. But the hours must be reported in seconds, and you wind up getting 43 million joules. This is a really large number because we're talking about joules, which are an extremely tiny amount of energy. You eat 10 million joules a day. In everyday life, we don't use meters a second. That's fine for the physics classroom, but in the real world, we use kilometers and hours. So the same thing applies here. We bundle into kilowatt hours. If I give you the formula E equals power times time, joules per second by the time they're running, what can we do with this? We have energy flow rate, which is joules per second, or dollars an hour, kilometers an hour. It's a rate. You multiply that rate by the time the activity takes place or how long the appliance is on for, and you will get your total energy. So the prior example said 3,000 watts times 4 hours. In the physics classroom, we would leave this in joules per second, which is a watt, and the 4 hours would turn to seconds. But in the industrial or engineering world or in the household world, these numbers are too tiny. The measurements will lead to gigantic answers like measuring your weight in milligrams. So instead, we bundle the watts to kilowatts. $3,000 becomes 3 grand. 3,000 meters becomes 3 kilometers. 3,000 watts becomes 3 kilowatts. And the 4 hours, we just don't convert it to seconds. So we wind up with a total energy calculation of 12 kilowatt hours. And that is joules, but it's hidden because this is a joule per second multiplied by the time it is running. This is saying a total energy equivalent to a 12,000 watt light bulb left running for 1 hour. That's how you read a kilowatt hour to understand it is a total energy being shown. What if you want it back in joules? It is one of the simplest conversions going. 12K becomes 12,000. 1 hour changes to 3,600 seconds. Between K and the H, that's 3,600,000. So you're literally just going to take your calculator, go 12 times 1,000 times 3,600, and you're in joules. Heck, if you round this out to like 3,000, you could ballpark it just in your head. Let's take a look at a household situation. You leave a 100-watt light bulb on in your bedroom for 8 hours. What energy did it use? In the scientific method, staying with proper base units, you would be forced to make a conversion on the time. And for some idiot reason, I make the correct conversion here, 100 joules per second. 8 hours turns to seconds, and I repeated it, and I don't know why. But I'm not going to change it now because these animations take forever to create. So I thought it was so good to show this setup, I did it twice. You multiply it out, and you get roughly 29,000 kilojoules. Now what about the real world calculation? In this case, you spare yourself the conversion. You just leave time alone. But 100 watts is 0.1 kilowatts. You need to bundle this in 1,000. Money, that would be $1,000. If I said you're doing a travel down the road 100 meters, I could also say 0.1 kilometers. You multiply these two and you get 0.8 kilowatt hours. I guarantee you these two numbers are the same. If you take this 0.8, multiply it by 1,000, and then multiply it by 3,600 seconds, you will get this answer. Okay, and I guarantee you, if you take this up here and you fail to do this conversion, all right, so this means divide by 3,600, divide by 100, and this number will turn into that one. They're the same. Now, kilowatt hours is a total. That would be what your house is built on. But the town of Orangeville might be megawatt hours by the end of the year, or gigawatt hours. They might even go to megawatt years. They're just simply going to say, how long did we leave the tap on? What's the flow rate and the time it was left on? What does this allow us to do with this formula now? Let's suppose you're given an answer 10 kilowatt hours. There's two things you can do with it. One, convert it to joules. Now there's a little bit of a problem here in my animation, so I'm going to ditch my animation. 10 kilowatts, you simply change the K to 1,000. So I throw on 3 extra zeros, and the hour becomes 3,600 seconds. This little multiply sign, I don't know why, just vanishes here when I present the show. So quick conversions gives us 36 million watt seconds. And you might go, well, what is a watt second? It's a joule. Look it. A watt, by definition, is a joule per second. So a joule per second times seconds is just joules. So if you notice you've got units of watt seconds, just write out what a watt really is, and you realize it's a joule. So we got 36 million joules. The other thing we might want to do is price it out. In Ontario, electricity is currently 13.4 cents per kilowatt hour at maximum. So